So here's something worth thinking about as you settle in tonight. Every single object that human beings have ever launched into space, every satellite, every capsule, every rover rolling across the dust of another world, all of it traces back to a very simple, very old idea. The idea that if you throw something hard enough, it doesn't come back down. That's it. That's the seed of everything. And people figured that out long before they had any way to act on it. Centuries before. Which means that for a really long time, space travel lived entirely in the human imagination, waiting for the engineering to catch up. And the story of how it finally did, how we went from watching the stars and wondering to actually going there, is one of the most extraordinary stories in all of engineering. Maybe in all of human history. And it's a good one to fall asleep to, because it's long and it's full of fascinating detours, and if you drift off somewhere over the early rocket experiments, that's perfectly fine. The stars will still be there. Let's start where it actually starts, which is not where most people think. It's not the 1960s. It's not even the 20th century. If you want to find the earliest roots of space exploration, you have to go back to China, roughly the 13th century, maybe a little earlier. The exact dates are debated, but somewhere around the year 1200, Chinese engineers, and they really were engineers, brilliant ones, figured out that if you packed a tube with gunpowder and left one end open, the expanding gases shooting out the back would push the tube forward. That's a rocket. That's Newton's third law in action, except Newton wouldn't be born for another 400 years. They didn't have the physics to explain why it worked, but they could see that it worked, and they used it, mostly for warfare. Fire arrows strapped to bamboo sticks, launched at enemy formations. There are records of these being used in battles as early as 1232, during the siege of Kaifeng, when the Jin dynasty used them against Mongol invaders. Imagine that for a second. You're a soldier in the 13th century, and suddenly there are screaming, flaming projectiles arcing through the sky at you. It must have been terrifying. Now, those early rockets were wildly inaccurate. They tumbled, they veered off course, sometimes they exploded before they left the launcher. But the core principle was sound, and it's the same principle that powers every rocket that's ever flown, right up to the ones launching today. You throw mass out the back, and the rocket goes forward. Action and reaction. It doesn't matter whether you're burning gunpowder in a bamboo tube or liquid hydrogen in a space shuttle main engine. The physics is identical. And here's what's really elegant about rockets compared to, say, a propeller or a jet engine. A rocket carries its own oxidizer. It doesn't need air, which means it works in a vacuum, which means it's the only type of engine that can actually function in space. That's not a coincidence. It's why rockets are the key to everything that follows. For a few hundred years after those Chinese fire arrows, rockets stayed mostly in the realm of weapons and fireworks. They spread along trade routes to the Middle East, to Europe. By the late 1700s, the Kingdom of Mysore in southern India was using iron-cased rockets against the British East India Company with devastating effectiveness. These Mysorean rockets, developed under the rule of Hyder Ali and his son Tipu Sultan, were a genuine military innovation. The iron casing let them hold more propellant and generate more thrust than anything the Europeans had seen. When the British finally captured some of these rockets after the fall of Seringapatam in 1799, they were so impressed that they brought them back to England and handed them to a military engineer named William Congreve. And Congreve, working at the Royal Arsenal at Woolwich, spent years reverse engineering and improving on the Mysorean design. By 1806, he had developed the Congreve rocket, which the British used extensively in the Napoleonic Wars and famously in the bombardment of Fort McHenry in 1814, which is why the American national anthem mentions the rocket's red glare. That's a direct line from 13th century China through 18th century India to a battle in Baltimore. Engineering doesn't happen in isolation. It migrates. It cross-pollinates. It builds on what came before. But here's the thing. All of those rockets, from the fire arrows to Congreve's weapons, were solid fuel rockets. You packed the propellant in, you lit it, and that was that. You couldn't throttle them. You couldn't shut them off and restart them. You couldn't really control the burn at all. For weapons, that was fine. You pointed them in roughly the right direction and hoped for the best. But for space travel, you need control. You need to be able to adjust your thrust, manage your trajectory, maybe shut down and reignite. And that requires a completely different kind of rocket. A liquid fuel rocket. And the story of how liquid fuel rocketry came to be is really the story of three men working independently in three different countries, all obsessed with the same impossible dream. The first of them, chronologically, is a Russian schoolteacher named Konstantin Tsiolkovsky. Born in 1857 in a small village, he lost most of his hearing to scarlet fever when he was about 10 years old. That changed the course of his life. He couldn't attend regular school, so he educated himself, spending years in libraries, devouring books on mathematics and physics. Eventually, he became a provincial school teacher, and in his spare time, which was considerable because he lived in relative obscurity for most of his life, he thought about space. Not in a vague, dreamy way, in a rigorous, mathematical way. In 1903, the same year the Wright brothers flew at Kitty Hawk, Tsiolkovsky published a paper called Exploration of Outer Space by Means of Rocket Devices. And in that paper, he derived what's now known as the Tsiolkovsky rocket equation. This is one of the most important equations in all of aerospace engineering, and it's worth understanding, at least intuitively, because it governs everything about how rockets work. Here's what it says, in plain language. The amount you can change your rocket's velocity, engineers call this delta V, depends on two things: the speed at which your exhaust leaves the rocket and the ratio of your rocket's total mass at the start, fully fueled, to its mass at the end, after the fuel is burned. That's it. Those are your two levers. If you want to go faster, you either need to push your exhaust out the back faster, or you need a higher ratio of fuel to everything else. And that second part is the cruel one, because it's logarithmic. To get a little more delta V, you need a lot more fuel. And that extra fuel has mass, which means you need even more fuel to lift that fuel, which means you need more fuel to lift that fuel, and you can see where this is going. It's a vicious cycle. Tsiolkovsky understood this completely, and he proposed the solution that we still use today: staging. You build your rocket in sections, and when the bottom section burns out, you throw it away. You literally drop the empty tanks and engines, shedding all that dead weight, so the remaining stages don't have to carry it. Every rocket that's ever reached orbit has used this principle. It's inescapable. The math demands it. Tsiolkovsky also proposed using liquid hydrogen and liquid oxygen as propellants, which turned out to be an incredibly prescient suggestion. He wrote about space stations, about airlocks, about growing food in space, about eventually colonizing the solar system. He was decades ahead of everyone. But he was a school teacher in rural Russia, publishing in obscure Russian journals. and almost nobody in the wider world knew about his work during his lifetime. He didn't build rockets. He didn't have the resources. He did the theory beautifully and correctly, and then history mostly forgot about him until the Soviet Union later adopted him as a hero of their space program, which he deserved. The second of our three dreamers is the one most Americans have heard of, and he had a very different kind of story. Robert Goddard was born in Worcester, Massachusetts in 1882, and he was obsessed with space from childhood. He later wrote about a specific moment, October 19th, 1899, when he climbed a cherry tree in his backyard and looked up at the sky and imagined traveling to Mars. He called it his anniversary day and marked it privately for the rest of his life. That kind of romantic fixation drove him, but it also made him secretive and prickly, because he was terrified that people would steal his ideas, or worse, laugh at him. And they did laugh at him. In 1920, the New York Times published an editorial mocking Goddard's suggestion that a rocket could work in the vacuum of space, claiming he lacked the knowledge ladled out daily in high schools, specifically that there was nothing in space for the exhaust to push against. The Times was wrong, embarrassingly wrong, and they eventually published a correction. In 1969, the day after Apollo 11 launched. But by then, Goddard had been dead for 24 years. Here's what Goddard actually did, though, that matters so much. On March 16th, 1926, in a snowy field on his Aunt Effie's farm in Auburn, Massachusetts, he launched the first liquid-fueled rocket in history. It was a spindly, ungainly thing, about 10 feet tall, with the engine mounted at the top and the fuel tanks hanging below, which looked strange but made sense to him at the time for stability reasons. It burned gasoline and liquid oxygen. It flew for about 2.5 seconds. It reached an altitude of roughly 41 feet, and it landed in a cabbage patch 84 feet away. By any practical measure, it was a laughable flight. But think about what that means. Think about what he actually demonstrated. He proved that a liquid fuel rocket engine could be built, could be ignited, could generate thrust, and could fly. Everything that came after, every orbital launch, every moon landing, every Mars rover, descends from that 2.5-second flight in a Massachusetts cabbage patch. Goddard kept working through the 1930s, moving to Roswell, New Mexico, for better weather and more privacy. He developed gyroscopic stabilization systems, vane-based thrust vectoring, fuel pumps, all sorts of innovations that would later show up in much larger rockets. But he worked in near total secrecy, patenting everything but publishing almost nothing, sharing his results with almost no one. He was brilliant, but isolated, and that isolation meant that when the really serious rocket work started happening in Europe, the people doing it had to figure out many of the same things independently. Which brings us to the third dreamer, and in some ways, the most consequential one, at least for the immediate story of space exploration. Hermann Oberth was born in 1894 in Transylvania, which was then part of Austria-Hungary. Like Tsiolkovsky, he worked out the mathematics of spaceflight independently. Like Goddard, he was consumed by the dream. In 1923, he published a book called The Rocket into Planetary Space, which laid out the theory of multi-stage rockets, orbital mechanics, and even the possibility of electric propulsion. The book was rigorous, visionary, and, crucially, widely read in Germany. It inspired an entire generation of young German engineers and enthusiasts, including a teenage boy named Werner von Braun, who would go on to become arguably the most important rocket engineer of the 20th century. But von Braun's story is complicated and dark in places because the road from amateur rocketry clubs in 1930s Berlin to the Saturn V that carried astronauts to the moon runs directly through the darkest chapter of the Second World War. And that's not something to gloss over, because understanding who von Braun was and what he was willing to accept tells you something important about the relationship between engineering ambition and moral compromise, a tension that runs through the entire history of space exploration, right up to the present day. So let's talk about young Werner. He was born in 1912 in Virsitz, in what was then the German Empire. His family was aristocratic. His father was a baron, a government minister. His mother gave him a telescope when he was confirmed, and that, combined with reading Obert's book, apparently set the course of his entire life. By the time he was 18, he joined the Verein für Raumschifffahrt, the Society for Space Travel, an amateur rocketry club in Berlin that was doing genuinely interesting experimental work. They were launching small liquid fuel rockets from an abandoned ammunition dump on the outskirts of the city, a place they called the Raketenflugplatz, the rocket airfield. It was scrappy, underfunded, and wildly enthusiastic, the way the best early-stage engineering work often is. They were figuring things out by trial and error, blowing things up, redesigning, trying again. But here's the thing about rocketry in the early 1930s. It was expensive, and the Weimar Republic was broke. The only institution with both the money and the motivation to fund serious rocket development was the military. Specifically, the German Army's Ordnance Department, which had a very particular interest in rockets. See, the Treaty of Versailles, signed after the First World War, placed strict limits on Germany's artillery, the range and caliber of guns they were allowed to build. But the treaty said nothing about rockets, because in 1919, military rockets weren't really a thing yet. Nobody thought to ban them. So the German military saw rockets as a loophole, a way to develop long-range weapons without technically violating the treaty. And when they came looking for talented young engineers, von Braun was right there, eager, brilliant, and willing. He joined the Army's rocket program in 1932 at the age of 20. By 1934, he'd earned his doctorate in physics. His thesis was on liquid propellant rocket combustion, and it was immediately classified. He was working at a secret facility at Kummersdorf, south of Berlin, under a career Army officer named Walter Dornberger, who became his patron and protector within the military bureaucracy. And together, they began building increasingly powerful rockets. The A-1, the A-2, the A-3, each one a step up in size, complexity, and capability, each one teaching them something new about combustion chamber design, propellant injection, guidance, aerodynamics. By 1936, the program had outgrown Kummersdorf, and they needed somewhere bigger, somewhere remote. Von Braun's mother, of all people, suggested a spot on the Baltic coast that his father used to go duck hunting, a place called Peenemünde. The military agreed, and what they built there was extraordinary. Peenemünde became one of the most advanced research and development facilities in the world. Wind tunnels, test stands, a liquid oxygen production plant, housing for thousands of engineers and technicians, all of it dedicated to one goal: building a long-range ballistic missile. The rocket they created was the A-4, though the world would come to know it by its propaganda name, the V-2, short for Vergeltungswaffe 2, Vengeance Weapon 2. And from a pure engineering standpoint, the V-2 was a staggering achievement. Think about what they accomplished. This was a rocket about 46 feet tall, burning a mixture of liquid ethanol and liquid oxygen, generating around 56,000 pounds of thrust. It could carry a roughly 2,000-pound warhead to a target over 200 miles away, reaching altitudes of 50 miles or more, the edge of space, essentially, and arriving at its target faster than the speed of sound, which meant you couldn't hear it coming. There was no defense against it, no warning. The engineering challenges they solved to make this work were immense. The combustion chamber had to handle temperatures around 2,500 degrees Celsius without melting, so they developed a regenerative cooling system where the ethanol fuel was circulated through a jacket around the chamber before being injected and burned, carrying heat away from the walls. The turbo pump that fed propellants into the chamber was driven by decomposing hydrogen peroxide through a catalyst, generating steam to spin the turbine. An elegant solution that Goddard had actually experimented with years earlier, though the Peenemünde team likely developed it independently. The guidance system used gyroscopes and an integrating accelerometer to cut off the engine at precisely the right moment, so the rocket would follow a ballistic arc to its target. It wasn't very accurate, it could miss by miles, but for hitting something the size of London, it didn't need to be accurate. Now, here's where the darkness comes in, and it's important to sit with this. The V-2 was built using slave labor. As the program moved into mass production in 1943 and 1944, the manufacturing was relocated to an underground factory called the Mittelwerk, carved into the Harz Mountains. The workers were concentration camp prisoners, primarily from a camp called Mittelbau Dora. The conditions were beyond horrific. Prisoners worked in tunnels with almost no ventilation, breathing toxic fumes, sleeping in the tunnels themselves in the early months. They were starved, beaten, worked to death. An estimated 20,000 people died in the production of the V-2. To put that in a grim perspective, more people died building the V-2 than were killed by the V-2 when it was used as a weapon. The rocket killed roughly 9,000 people in attacks on London, Antwerp, and other cities. 20,000 died making it. Von Braun's exact knowledge of and complicity in these conditions is debated by historians, but what's clear is that he visited the Mittelwerk. He was aware of the labor source, and he held the rank of Sturmbannführer in the SS, equivalent to a major. Whether he joined the SS out of genuine conviction or career necessity, whether he could have done anything to change the conditions or not, these are questions without clean answers. What is undeniable is that his engineering ambitions were realized on a foundation of extraordinary human suffering. And that's a fact that has to sit alongside everything else he accomplished, including the things he accomplished later for the United States. Because as the war ground toward its end in early 1945, von Braun and his team faced a choice. The Soviet army was advancing from the east, the Americans and British from the west. Von Braun organized the surrender of himself and about 500 of his top engineers to the Americans, reportedly reasoning that the United States was the country most likely to fund a space program. The Americans, for their part, were desperate to get their hands on German rocket technology before the Soviets did. The result was Operation Paperclip, a secret program that brought von Braun and more than 100 other German scientists and engineers to the United States, quietly whitewashing their wartime records to get around President Truman's order that no active Nazis be admitted. And the Soviets? They were doing exactly the same thing. They captured Peenemünde. They captured the Mittelwerk. They grabbed every V-2 component and every German engineer they could find. They shipped whole factories east. The Cold War space race, when it came, would be built on both sides from the bones of the V-2 program. So let's follow both threads for a moment, because they're going to converge in the most dramatic way imaginable. On the American side, von Braun and his team were initially sent to Fort Bliss, Texas, in the nearby White Sands Proving Ground in New Mexico, where they reassembled and launched captured V-2 rockets for research purposes. These launches were genuinely useful. Scientists strapped instruments to the rockets and sent them to the edge of space, gathering data on the upper atmosphere, cosmic rays, solar radiation. It was the first time anyone had been able to take measurements at those altitudes, but the program was modest, underfunded, and frankly, the American military wasn't quite sure what to do with these German rocketeers. Von Braun chafed. He wanted to build bigger rockets, go to space, go to the moon. The Army wanted battlefield missiles. On the Soviet side, the story centers on one of the most remarkable engineers of the 20th century, a man whose name was literally a state secret for most of his career, Sergei Pavlovich Korolev. And his story is, if anything, even more dramatic than von Braun's, because before he built the rockets that launched the space age, he survived something that should have killed him. Korolev was born in 1907 in Zhytomyr, in what is now Ukraine. Like von Braun, he was obsessed with flight from a young age. He became an aircraft designer, then got swept up in the excitement around rocketry in the early 1930s. He co-founded GERD, the Group for the Study of Reactive Motion, which was essentially the Soviet equivalent of the German amateur rocketry clubs. They launched the Soviet Union's first liquid fuel rocket in 1933. Korolev was brilliant, driven, visionary. He wrote papers about rocket-powered aircraft and crewed spaceflight. He was exactly the kind of person the Soviet Union needed. And then, in 1938, during Stalin's Great Purge, he was arrested. The charges were essentially fabricated: sabotage, membership in a counter-revolutionary organization. He was tortured during interrogation. His jaw was broken. He was sentenced to 10 years of hard labor and sent to the Kolyma gold mines in Siberia, one of the most brutal camps in the entire Gulag system. Kolyma had a mortality rate that was staggering. Korolev nearly died there, from exhaustion, from scurvy, from the cold. He lost most of his teeth. His heart was permanently damaged. He was eventually transferred to a sharashka, a special prison where scientists and engineers were put to work on military projects while still technically serving their sentences. He worked under the aircraft designer Andrei Tupolev, who was himself a prisoner. Think about that for a moment. The Soviet Union imprisoned its best engineers, nearly killed them, and then expected them to design advanced weapons. It's a level of institutional madness that's hard to fully comprehend. Korolev was released in 1944 and formally rehabilitated after the war, but the experience marked him for life. His health never fully recovered. And yet, when the captured V-2 technology began arriving from Germany, Korolev threw himself into the work with an intensity that bordered on obsession. He studied the V-2, understood its strengths and limitations, and then set about building something better. His first major project was the R-1, essentially a Soviet copy of the V-2, reverse-engineered from captured components and documentation. But Korolev wasn't interested in copies. He was already thinking beyond the V-2, already sketching designs for rockets powerful enough to reach orbit, powerful enough to carry warheads across continents, powerful enough to change the world. And that's exactly what he did. The R-2 came first, essentially a stretched and improved V-2 with roughly double the range, about 600 kilometers. But even as the R-2 was being tested, Korolev was pushing for something far more ambitious. He wanted an intercontinental ballistic missile, an ICBM, something that could carry a nuclear warhead from Soviet territory all the way to the United States. and the Soviet military wanted exactly the same thing, which meant Korolev had something that Goddard never really had, and that von Braun had only intermittently: genuine, sustained, high-priority government backing. Now, here's the thing about designing an ICBM in the early 1950s. The problem wasn't just building a powerful rocket. The problem was that Soviet nuclear warheads were heavy. Really heavy. The Americans had been miniaturizing their warheads, making them lighter and more compact, which meant their rockets didn't need to be as powerful. But the Soviet warheads at that time weighed several tons. So Korolev needed a rocket with an enormous amount of thrust, far more than anything that had ever been built. And his solution was elegant in a way that would have enormous consequences for the future of spaceflight, even though that wasn't the original intent. The rocket he designed was called the R-7, and it's one of the most important machines ever built. Let me walk you through it, because the engineering is genuinely beautiful. Instead of trying to build a single engine powerful enough to lift this massive payload, Korolev used a cluster approach. The R-7 had a central core stage surrounded by 4 strap-on boosters, each one essentially a rocket in its own right. Together, the 5 sections contained a total of 20 main combustion chambers, 4 in each of the 5 units, all burning liquid oxygen and kerosene. At liftoff, all 20 chambers fired simultaneously, producing roughly 400 tons of thrust. That's an extraordinary number for the mid-1950s. The strap-on boosters would burn for about 2 minutes, then separate and fall away, leaving the central core to continue on its own. It was staging, just like Tsiolkovsky had described half a century earlier, but implemented in a way that was mechanically ingenious. And here's what's really clever about the design. Each of the 5 rocket units used the same basic engine, the RD-107 for the boosters and the slightly modified RD-108 for the core. These engines were designed by Valentin Glushko, another towering figure in Soviet rocketry, and incidentally, a man who had a complicated and sometimes hostile relationship with Korolev. Glushko had also been arrested during the purges, had also survived the Sharashka system, and had his own vision for how Soviet rockets should be built. He and Korolev clashed repeatedly over propellant choices. Glushko favored storable hypergolic fuels that ignite on contact, while Korolev insisted on liquid oxygen and kerosene, which he considered safer and more powerful for large vehicles. Their rivalry would shape Soviet space engineering for decades. But in the early 1950s, they were still collaborating, and the engines Glushko designed for the R-7 were remarkable. They used a staged combustion cycle, where the turbopump exhaust gases were fed back into the combustion chamber rather than being dumped overboard. This made the engines significantly more efficient than their American counterparts. It's a design philosophy that Russian rocket engines still use today. In fact, when the Soviet Union collapsed and American engineers finally got to examine Russian engines up close, they were stunned by how good they were. The RD-180, a direct descendant of Glushko's work, ended up powering the American Atlas V rocket for years. Think about that. Decades after the space race, American rockets were flying on engines whose lineage traced straight back to Glushko's workshop. So the R-7 was being developed primarily as a weapon, a way to deliver nuclear warheads across oceans. But Korolev understood something else about it. He understood that a rocket powerful enough to hurl a multi-ton warhead across continents was also powerful enough to put something into orbit. And he began quietly lobbying the Soviet leadership to let him try. This wasn't easy. The military wanted their missile. They didn't particularly care about satellites or space exploration. But Korolev was persuasive, and he had a powerful argument: Putting a satellite in orbit before the Americans would be an enormous propaganda victory. It would demonstrate Soviet technological superiority to the entire world. Meanwhile, on the American side, things were moving more slowly, and for reasons that seem almost absurd in retrospect. The United States had actually announced plans to launch a satellite as part of the International Geophysical Year, a coordinated global scientific effort running from July 1957 to December 1958. But instead of giving the job to von Braun and his team at the Army Ballistic Missile Agency, who had the most powerful rockets and the most experience, the project was awarded to the Naval Research Laboratory and their Vanguard rocket. The reasoning was partly political. The Eisenhower administration wanted the satellite program to appear civilian and scientific rather than military, and von Braun's team was too closely associated with the Army's ballistic missile program. There was also, frankly, a lingering discomfort with von Braun's past. Handing America's first space achievement to a former SS officer who had built weapons for Hitler wasn't an appealing narrative. So von Braun waited, frustrated, while the Vanguard program moved forward at a cautious, methodical pace. His team had actually demonstrated that they could reach orbital velocity as early as 1956. They launched a Jupiter-C rocket that could have put a satellite in orbit if it had carried one, but they'd been explicitly ordered not to. The fourth stage that would have done the job was deliberately filled with sand instead of propellant. Von Braun was furious. He knew the Soviets were coming. He could feel it. And he was right. On October 4th, 1957, the R-7 roared off its launch pad at the Baikonur Cosmodrome in Kazakhstan, carrying a small polished metal sphere about the size of a beach ball with 4 trailing antennas. Sputnik. It weighed just 83.5 kilograms. Tiny compared to what the R-7 could carry. But that was the point. Korolev had deliberately kept it simple so there would be fewer things to go wrong. The satellite did almost nothing. It carried a radio transmitter that sent out a steady beep, beep, beep on frequencies that any amateur radio operator on Earth could pick up. And that was enough. That simple beep changed everything. The reaction in the United States was something close to panic. And I don't use that word lightly. Americans looked up at the night sky and knew that a Soviet object was passing overhead, and if the Soviets could put a satellite up there, they could put a nuclear weapon up there. The psychological impact was enormous. Eisenhower tried to downplay it. He called Sputnik one small ball in the air, but the public wasn't buying it. Newspapers ran headlines about Soviet superiority. Politicians demanded answers. How had the Russians beaten us? What had gone wrong? And then it got worse. A month later, on November 3rd, the Soviets launched Sputnik 2, and this time the payload wasn't a simple beeping sphere. It was a dog, a stray from the streets of Moscow named Laika, strapped into a pressurized compartment with enough food and oxygen for several days. Laika was never meant to come back. There was no re-entry system. The official Soviet story for years was that Laika survived for about a week before being painlessly euthanized by a timed injection. The truth, which didn't emerge until 2002, was that Laika died within hours of reaching orbit, probably from overheating and stress. It's a painful story. She was a good-natured dog who had been chosen partly because of her calm temperament, and she died alone in a tiny capsule 400 miles above the Earth. The mission provided valuable data about how a living creature responded to spaceflight, the launch forces, the weightlessness. But the cost was real, and it should be acknowledged. The Americans, desperate to respond, pushed the Vanguard rocket forward. On December 6, 1957, with the entire nation watching on live television. And this is important because the Soviets conducted their launches in secret and only announced successes. The Vanguard rocket rose about 4 feet off the launch pad, lost thrust, settled back down, and exploded in a spectacular fireball. The tiny satellite it carried was thrown clear of the wreckage and landed in nearby bushes, its transmitter still pathetically beeping. The press called it Flopnik and Kaputnik and Stayputnik. It was a national humiliation. Now, finally, the call went to von Braun, and he was ready. He'd been ready for over a year. His team worked at a frantic pace, and on January 31st, 1958, a Juno 1 rocket, essentially the Jupiter C that had been denied its chance 2 years earlier, successfully placed Explorer 1 into orbit. America was in space, and Explorer 1 actually made a genuine scientific discovery. It carried a Geiger counter designed by James Van Allen of the University of Iowa, and the instrument detected belts of intense radiation trapped by Earth's magnetic field, the Van Allen radiation belts. So America's first satellite wasn't just a political statement. It actually found something new about the planet. But the damage was done in terms of perception. The Soviets had been first, and that mattered enormously in the context of the Cold War. Sputnik triggered a cascade of consequences. The United States created NASA in 1958, consolidating its scattered space efforts into a single civilian agency. Congress passed the National Defense Education Act, pouring money into science and engineering education. The entire American relationship with technology and education shifted because of a beeping metal ball. And Korolev wasn't done. Not even close. He was already thinking about the next step, the step that everyone knew was coming, but that seemed almost impossibly dangerous. If you could put a dog in orbit, you could put a person in orbit. The question was whether that person would survive, and whether you could bring them home. The engineering challenges were immense. You needed a spacecraft that could protect a human being from the vacuum of space, from temperature extremes, from radiation, from the crushing forces of launch and the searing heat of re-entry. You needed life support systems that could provide oxygen and remove carbon dioxide. You needed a heat shield that could withstand temperatures of several thousand degrees as the capsule slammed back into the atmosphere. You needed a way to control the spacecraft's orientation so the heat shield faced the right direction during re-entry. And you needed all of this to work perfectly, every single time, because there was no margin for error when a human life was at stake. Korolev's answer was the Vostok spacecraft, and it was designed with a philosophy that tells you a lot about how Soviet engineers thought about reliability. The capsule was a sphere, the simplest possible shape for re-entry, because a sphere is inherently stable no matter what orientation it enters the atmosphere in. You don't need to worry about pointing it the right way if every direction is the same. The cosmonaut sat inside this sphere in an ejection seat, and here's a detail that the Soviets kept secret for years. The plan was for the cosmonaut to eject from the capsule at about 7 kilometers altitude and parachute down separately, because the spacecraft's own parachute system couldn't slow it down enough for a safe landing. This mattered because the international body that certified aviation records required that the pilot land inside the aircraft for the flight to count as an official record. So, the Soviets simply lied about it. They said Gagarin landed inside the capsule. The truth didn't come out for years, and by then it didn't really matter, because the achievement itself was undeniable. On April 12, 1961, Yuri Gagarin became the first human being to leave the Earth and return alive. Let's stay with that morning for a moment, because it deserves it. Gagarin was 27 years old. He was a fighter pilot, compact, 5'2", which actually mattered because the Vostok capsule was tiny. He'd been selected from a group of 20 cosmonauts, and the final choice between him and his backup, German Titov, came down partly to personality. Gagarin had this extraordinary warmth about him, a smile that people described as infectious, a calm that felt genuine rather than performed. Korolev liked him. The selection committee liked him. He was the son of a carpenter and a milkmaid from a village west of Moscow. And there was something about that background that appealed to the Soviet narrative, of course. But by all accounts, Gagarin was genuinely well liked by everyone who knew him. The launch happened from Baikonur, in the Kazakh steppe. Gagarin rode the elevator up to the capsule, climbed in, and waited. There was a delay. A hatch sensor indicated it wasn't sealed properly, so technicians had to remove and reseat 30 screws to fix the seal. Imagine that. You're sitting in a metal sphere on top of a rocket, about to attempt something no human has ever done, and a technician is outside with a screwdriver. Gagarin apparently stayed calm through the whole thing. When the engines finally ignited, those same RD-107 and RD-108 engines we talked about, Glushko's staged combustion design, Gagarin said one word into his radio. "Poyakali, let's go." The flight lasted 108 minutes, one orbit. Gagarin didn't actually control the spacecraft for most of the flight. The controls were locked because engineers weren't sure whether a human could function normally in weightlessness. They genuinely didn't know if the disorientation of zero gravity might cause a pilot to panic or make irrational decisions. So they gave him a sealed envelope with the unlock code, just in case. He needed it only for emergencies. As it turned out, Gagarin was fine. He reported that weightlessness felt pleasant. He looked out the window and described the Earth, the blue halo of the atmosphere, the shadows of clouds on the ocean. He ate and drank from tubes to prove it was possible. And then, after one orbit, the retro-rocket fired to slow the capsule for re-entry. And here's where things got genuinely terrifying. The service module, the equipment section attached to the back of the spherical capsule, was supposed to separate cleanly after the retro-rocket burn. It didn't. A bundle of cables and a metal strap held the two sections together, and as the spacecraft hit the upper atmosphere, the whole assembly started tumbling wildly. Gagarin was being whipped around, experiencing about 8 Gs, with the capsule and the service module connected by this stubborn tether, spinning end over end. The heat of re-entry eventually burned through the connection, and the service module broke free, and the capsule stabilized, the sphere doing exactly what it was designed to do, finding its own stable orientation regardless of how it entered the atmosphere. But for about 10 minutes, Gagarin was in a situation that could easily have killed him, and he stayed calm. He reported what was happening. He didn't panic. At about 7 kilometers, the hatch blew off, and Gagarin ejected. He parachuted down into a field near the Volga River, near the city of Saratov. He landed near a farmer and her granddaughter, who were understandably startled to see a man in an orange flight suit and a white helmet descending from the sky. And just like that, the space age had a human face. Now think about the reaction in the United States. It was Sputnik all over again, but worse. Sputnik was a beeping ball. This was a person. The Soviets had put a man in orbit and brought him home, and America hadn't even attempted it yet. The psychological impact was enormous. President Kennedy had been in office for less than 3 months, and he was already dealing with the Bay of Pigs disaster in Cuba. He needed a win. He needed something bold enough to change the narrative. And on May 25, 1961, just 6 weeks after Gagarin's flight, Kennedy stood before Congress and made one of the most consequential declarations in the history of engineering. He committed the United States to landing a man on the moon and returning him safely to Earth before the end of the decade. Think about what that meant in practical terms. In May of 1961, the total American experience with human spaceflight was Alan Shepard's 15-minute suborbital hop, which had happened just 3 weeks earlier. Shepard went up, came down. He didn't even orbit. And Kennedy was saying, "We're going to the moon within 9 years." The gap between where they were and where they needed to be was almost incomprehensible. But here's the thing about Kennedy's decision. It wasn't just inspirational rhetoric. It was an engineering commitment backed by an engineering plan. And the person who would have to make it real was already in place. Wernher von Braun had been thinking about moon missions for years, decades really, going all the way back to his days in the German Rocket Society. He'd written papers about it. He'd appeared on Walt Disney's television show in the 1950s, explaining to millions of Americans how a moon mission would work, complete with beautiful illustrations of rotating space stations and sleek lunar landers. Von Braun had been waiting for this moment his entire career. But dreaming about going to the moon and actually figuring out how to do it are very different things, and the first big engineering argument was about the mission architecture. How do you actually get to the moon and back? There were 3 main proposals. The first was called direct ascent. You build one enormous rocket, fly it straight to the moon, land the whole thing on the lunar surface, and then launch it back to Earth. Simple in concept, but the rocket you'd need would be absolutely colossal. A vehicle called Nova that would have dwarfed anything ever built. Von Braun initially favored this approach, or something close to it. The second approach was Earth orbit rendezvous. You'd launch multiple rockets, assemble a moon-bound spacecraft in Earth orbit, and then head for the moon. This was more practical in terms of rocket size, but it required mastering orbital rendezvous and docking, which nobody had ever done. The third approach was the one that actually won, and it was championed by a man named John Houbolt, an engineer at NASA's Langley Research Center. His idea was lunar orbit rendezvous. Instead of taking the entire spacecraft down to the moon's surface, you'd go into orbit around the moon, send a small, lightweight lander down to the surface with just 2 astronauts, and leave the main spacecraft orbiting above with the 3rd crew member. After the surface mission, the lander would launch back up, dock with the orbiting spacecraft, and everyone would come home together. Houbolt's idea was elegant because it dramatically reduced the weight you needed to land on the moon. You didn't have to bring all that fuel for the return trip to Earth, down to the lunar surface and back up again. You left it in orbit. The weight savings cascaded through the entire mission design. A smaller lander meant a smaller rocket to get everything to the moon, which meant a smaller rocket to get everything off the Earth. It was the kind of insight that seems obvious in hindsight, but was genuinely controversial at the time. Houbolt had to fight for it. He went around the normal chain of command, writing directly to senior NASA officials, which was considered presumptuous. Some engineers thought the idea was too risky. What if the rendezvous in lunar orbit failed? You'd have astronauts stranded around the moon with no way home. But the math was compelling, and eventually, in 1962, NASA committed to lunar orbit rendezvous. It was one of the most important engineering decisions of the entire Apollo program, and it was made by a guy who had to basically pester his way to being heard. So now NASA had a plan, and they needed hardware. The rocket would be the Saturn V, von Braun's masterpiece, developed at the Marshall Space Flight Center in Huntsville, Alabama. And the Saturn V, let's just sit with this machine for a moment, because it remains one of the most extraordinary things human beings have ever built. It stood 363 feet tall. That's taller than the Statue of Liberty, including the pedestal. Fully loaded with fuel and payload, it weighed about 6.5 million pounds. The Mars first stage, called the SIC, was powered by 5 F-1 engines, each one generating 1.5 million pounds of thrust. 5 of them together produced 7.5 million pounds of thrust at liftoff. To this day, the F-1 remains the most powerful single-chamber liquid-fueled rocket engine ever flown. Each engine burned about 3 tons of kerosene and liquid oxygen per second. The sound at launch was so intense that it could be heard from over 100 miles away, and the acoustic energy was powerful enough to cause physical pain if you stood too close. The engineering of the F-1 engine alone is a story worth lingering on. The biggest challenge was the combustion instability problem. When you're injecting enormous quantities of fuel and oxidizer into a combustion chamber and igniting them, the combustion process can develop oscillations, pressure waves that bounce back and forth inside the chamber, reinforcing each other, growing stronger with each cycle. It's a bit like the way sound can resonate in a pipe organ, except instead of music, you get an explosion. These instabilities could tear an engine apart in milliseconds. And the bigger the engine, the worse the problem. The F-1 was so large that conventional approaches to combustion stability simply didn't work at that scale. The engineers at Rocketdyne, the company that built the F-1, spent years fighting this problem. They developed a method that was almost absurdly direct. They would deliberately set off small bombs inside the combustion chamber while the engine was running, to see how the combustion responded to the disturbance. If the oscillations damped out quickly, the design was stable. If they grew, back to the drawing board. They tested and redesigned the injector plate, the component that sprays fuel and oxidizer into the chamber, over and over, tweaking the pattern of injection holes, adjusting the baffles that divided the injector face into compartments. It took more than 2,000 individual test firings to get the F-1 combustion chamber stable enough for human-rated flight. 2,000 tests. And each test meant bolting a massive engine to a test stand, filling it with propellant, lighting it, and measuring what happened. The persistence involved is almost hard to fathom. Above the first stage sat the S-2 second stage, powered by 5 J-2 engines burning liquid hydrogen and liquid oxygen. A much more efficient propellant combination, but also a much more difficult one to handle, because liquid hydrogen has to be kept at -423 degrees Fahrenheit. The insulation challenges alone were formidable. And above that, the S-4B third stage with a single J-2 engine, which would fire twice, once to reach Earth orbit, and then again to send the spacecraft on its trajectory toward the Moon, a maneuver called trans-lunar injection. The spacecraft itself had 2 main pieces. The Command and Service Module, built by North American Aviation, was where the 3 astronauts lived for most of the mission. A conical command module about 13 feet across at its base, attached to a cylindrical service module that carried the main engine, fuel cells for electrical power, and consumables. And then there was the lunar module, built by Grumman, which was the spidery, ungainly-looking craft that would actually land on the Moon. It had 2 stages, a descent stage with a throttleable engine for landing, and an ascent stage that would blast off from the Moon's surface using the descent stage as a launch pad. The lunar module didn't need to be aerodynamic because it would never fly through an atmosphere. It could be any shape that worked, and the shape that worked turned out to look like nothing anyone had ever imagined a spacecraft would look like. All angles and foil and spindly legs. But before any of this hardware could go to the Moon, NASA had to learn how to do the things the mission required. rendezvous, docking, spacewalks, long-duration flight, navigation in deep space, and that learning happened through two programs that preceded Apollo, Mercury and Gemini. Mercury was the first, the one that put Shepard and then John Glenn into space. Glenn's orbital flight in February 1962 was a huge moment for American confidence. But Mercury was limited. The capsule was tiny, a one-person vehicle with almost no maneuvering capability. It proved humans could survive in space and function, but it couldn't teach the skills Apollo would need. Gemini was different. Gemini was the program where NASA learned to actually fly in space, and the pace of it was extraordinary. Between March 1965 and November 1966, NASA flew 10 crewed Gemini missions. 10 missions in roughly 20 months. Think about that pace for a second. That's a new crewed spaceflight almost every other month, each one building on the last, each one pushing the envelope a little further. It was like a graduate school for orbital mechanics, compressed into less than 2 years, and the astronauts and engineers were writing the textbook as they went. The Gemini capsule itself was a significant step up from Mercury. It was still small, 2 astronauts crammed into a cabin with about as much room as the front seat of a Volkswagen Beetle. But it had something Mercury never did, the ability to change its orbit. Gemini carried an orbit attitude and maneuvering system, a set of thrusters that let the crew adjust their trajectory, raise or lower their orbit, change planes, and chase down another object in space. That maneuvering capability was everything, because if you're going to do lunar orbit rendezvous, if your whole moon mission depends on 2 spacecraft finding each other and docking while orbiting the moon 240,000 miles from home, you had better know how to rendezvous and dock before you go. The first crewed Gemini flight was Gemini 3 in March 1965, with Gus Grissom and John Young. It was a short flight, just 3 orbits, but it validated the spacecraft's systems, and importantly, Grissom fired the thrusters to change the orbital path. That was a first for an American spacecraft, actually maneuvering in orbit, deliberately altering your trajectory, rather than just riding along whatever path the booster put you on. It sounds simple, but it was a conceptual leap. You're not a passenger anymore. You're a pilot. But the really dramatic Gemini moments came quickly after that. Gemini 4, in June 1965, featured Ed White's spacewalk, the first American extravehicular activity. White floated outside the capsule for about 20 minutes, tethered by a golden umbilical, using a handheld gas gun to move around. He famously didn't want to come back in. "I'm coming back in," he finally said, "and it's the saddest moment of my life." The Soviets had beaten them to it. Alexei Leonov had done the first spacewalk 3 months earlier, during Voskhod 2, and Leonov's experience had been genuinely terrifying. His suit had ballooned in the vacuum so badly that he couldn't fit back through the airlock hatch. He had to partially depressurize his suit, risking decompression sickness, just to squeeze himself back inside. That detail didn't become widely known in the West for years, but it's a reminder that behind every triumphant first, there's usually a story of something nearly going catastrophically wrong. Now, here's where Gemini gets really interesting from an engineering standpoint. Gemini 6 and 7 were originally separate missions with different goals. Gemini 7, commanded by Frank Borman with Jim Lovell, was planned as a long-duration flight. 14 days in that tiny capsule, proving that humans could endure the length of time a moon mission would require. Gemini 6 was supposed to rendezvous with an unmanned Agena target vehicle, but the Agena exploded during launch in October 1965. So NASA, in a move that shows how nimble and bold the program was at the time, came up with an audacious alternative. Why not launch Gemini 7 first on its long-duration mission, and then launch Gemini 6 to rendezvous with Gemini 7? Two crewed spacecraft, meeting in orbit. It had never been done. Gemini 7 launched on December 4th, 1965. Then on December 12th, Gemini 6A, they added the A to denote the revised mission, sat on the pad ready to go. The engines ignited and then shut down after about 1 second. A plug had dropped out of the base of the rocket prematurely, triggering the shutdown. The mission rules said the crew should eject. There were ejection seats in Gemini, unlike the escape tower on Mercury and Apollo, but command pilot Wally Schirra made a split-second judgment call. He didn't feel the rocket moving. If the rocket wasn't actually lifting off, ejecting was more dangerous than sitting tight. So he stayed. It was one of those moments where a test pilot's instinct saved the mission, and possibly lives. They recycled, fixed the problem, and launched 3 days later on December 15th. And then Schirra and Tom Stafford in Gemini 6A performed the first true rendezvous in space, bringing their capsule to within about 1 foot of Gemini 7. 1 foot. They station kept for hours, the two spacecraft flying in formation, close enough that the crews could see each other through the windows. They didn't dock. Gemini 6A didn't have docking hardware. But they proved that rendezvous was possible, that a pilot could fly a spacecraft precisely enough to find another object in orbit and match its velocity and position. And that was the key skill. That was the thing that made lunar orbit rendezvous viable. Docking came next, on Gemini 8 in March 1966, and this is a mission worth spending a moment on because of what went wrong. The crew was Neil Armstrong, yes, that Neil Armstrong, and David Scott. They successfully docked with an unmanned Agena target vehicle, the first docking of 2 spacecraft in orbit. But shortly after docking, the combined vehicle started rolling. Armstrong undocked from the Agena, thinking the problem was with the target vehicle, but the roll got worse. Much worse. The Gemini capsule began spinning at about 1 revolution per second. At that rate, the crew was close to losing consciousness. Armstrong realized the problem was a stuck thruster on the Gemini spacecraft itself, not the Agena. He shut down the entire orbital maneuvering system and used the re-entry control thrusters, a separate, independent set of small jets normally reserved for controlling the capsule during re-entry, to stop the spin. It worked, but using those re-entry thrusters meant mission rules required an immediate return to Earth. The mission was cut short, but Armstrong's cool-headed troubleshooting under extreme physical stress was exactly the kind of performance that would later put him at the top of the list when NASA chose who would command the first moon landing. The later Gemini missions continued to build skills. Gemini 9 through 12 practiced more rendezvous techniques, more spacewalks, and the spacewalks were harder than anyone expected. Astronauts found that without handholds and footholds, every task in zero gravity turned into an exhausting wrestling match against Newton's third law. You try to turn a bolt, and your whole body rotates in the opposite direction. Gene Cernan, on Gemini 9A, had such a difficult spacewalk that his heart rate hit 180 beats per minute and his visor fogged completely. He could barely see. It was Buzz Aldrin, on the final mission, Gemini 12, in November 1966, who finally cracked the problem. Aldrin had trained extensively underwater, one of the first to use underwater neutral buoyancy simulation as a stand-in for zero gravity. And he insisted on proper body restraints being installed on the spacecraft exterior, handrails, foot restraints, tethers. With those tools, he performed his spacewalks smoothly and efficiently. The lesson was clear. Working in space isn't about strength or heroism. It's about preparation, tools, and understanding the physics of your environment. That lesson carried directly into Apollo and every spacewalk program since. So by the end of 1966, Gemini had taught NASA how to rendezvous, dock, walk in space, and endure long-duration flights. The toolbox was full. The Saturn V was coming together. The lunar module was being built. Everything was converging toward the moon. And then, on January 27, 1967, everything stopped. Apollo 1. The designation was originally AS-204, but after the disaster, it was retroactively named Apollo 1 in honor of the crew. Gus Grissom, Ed White, and Roger Chaffee were inside the command module on the launch pad at Cape Kennedy for a plugs-out test. A full rehearsal of the countdown sequence with the spacecraft running on its own internal power. It wasn't considered a particularly dangerous test. The rocket wasn't fueled, but the cabin was pressurized with pure oxygen at slightly above atmospheric pressure, and that detail was lethal. A spark, the exact source was never definitively identified, though it was likely an electrical arc in the lower equipment bay, ignited something in that pure oxygen environment, and the fire spread with horrifying speed. In pure oxygen at 16.5 pounds per square inch, materials that would barely smolder in normal air become ferociously flammable. Velcro, nylon netting, paper checklists, even the coolant fluid, all of it burned. The crew had no chance. The hatch was a complicated inward opening design that required ratcheting open with a special tool, a process that took about 90 seconds under ideal conditions. In a cabin filling with flame and toxic smoke, 90 seconds was an eternity. All 3 astronauts died, likely within 30 seconds of the fire's start, from cardiac arrest caused by the toxic atmosphere. The investigation that followed was devastating. It revealed that the command module had been plagued with problems, wiring issues, flammable materials throughout the cabin, coolant leaks, a hatch design that prioritized preventing accidental opening in space over rapid emergency egress on the ground. The review board's report was blunt. North American Aviation, the contractor, came under intense scrutiny. Joseph Shea, the brilliant but overworked Apollo spacecraft program office manager, was quietly moved to a different position. The entire command module was essentially redesigned. The hatch was replaced with a unified, quick-opening design that could be opened outward in about 5 seconds. Flammable materials were stripped out and replaced wherever possible. The cabin atmosphere for ground tests was changed to a nitrogen-oxygen mix instead of pure oxygen. Wiring was rerouted and better protected. More than 1,000 changes were made. It took 20 months of redesign, rebuilding, and soul-searching. The Soviet program suffered its own tragedy in April 1967, when Vladimir Komarov was killed during the return of Soyuz 1. The parachute system failed, and the capsule hit the ground at full speed. Komarov became the first person to die during a spaceflight. These losses on both sides were a brutal reminder that spaceflight was not a game, not a propaganda exercise, not an abstraction. Real people were climbing into machines filled with explosive propellants and trusting their lives to engineering decisions made by other fallible humans. But here's the thing about the Apollo 1 fire. And this is something that people who worked on the program have said many times since. As horrible as it was, the fire may have saved the moon program. Because the command module that existed before the fire probably would have failed during an actual mission. The problems were systemic, not isolated, The fire forced a complete reckoning, a top-to-bottom review that produced a vastly better spacecraft. Frank Borman, who served on the review board, later said that without the fire, they might never have gotten to the moon at all, or they might have lost a crew in a place where rescue was impossible. When Apollo flights resumed, they resumed with purpose and with a spacecraft that had been forged, in a terrible sense, by tragedy. Apollo 7, in October 1968, was the first crewed flight of the redesigned command module, and it worked beautifully. 11 days in Earth orbit, all systems performing. Wally Schirra commanded it, and while the crew famously clashed with mission control over scheduling and caught head colds that made them irritable, the spacecraft itself was solid. And then came a decision that still seems almost reckless in hindsight, one of the boldest calls in the history of human exploration. Apollo 8. Originally planned as a test of the lunar module in Earth orbit, the mission was radically redesigned when the lunar module fell behind schedule. Instead of waiting, NASA decided to send Apollo 8 all the way to the moon, without a lunar module, just the command and service module, to orbit the moon and come home. Frank Borman, Jim Lovell, and Bill Anders would be the first humans to leave Earth orbit, the first to see the far side of the moon with their own eyes, the first to experience the gravitational pull of another celestial body. And they would do it on only the third flight of the Saturn V, a rocket that had suffered serious problems on its second unmanned test, including pogo oscillations that nearly tore the vehicle apart and an engine that shut down prematurely. The decision to put humans on the very next flight and send them to the moon was a gamble of extraordinary proportions, driven partly by engineering confidence, partly by Cold War urgency. There were real concerns that the Soviets might attempt a crude lunar flyby first, and partly by something harder to define, a sense that the moment was right, that the team was ready. That waiting would mean losing momentum. And so, on December 21st, 1968, at 7:51 in the morning Eastern Time, the Saturn V lit up the Florida sky and pushed 3 men toward the moon. The flight took about 3 days to get there. Think about that. 3 days in a spacecraft roughly the size of a large car interior, hurtling through a void no human had ever crossed. The navigation was a marvel in itself. The onboard computer, the same basic design that would guide all Apollo missions, had about 74 kilobytes of memory. Your phone has millions of times more. But the software, written largely by a team at MIT, led by Margaret Hamilton, was elegant and robust, and the guidance equations worked beautifully. The crew also carried a sextant, yes, a sextant, the same basic instrument that sailors had used for centuries, and they could sight on known stars through a small telescope built into the command module to verify their position. Ancient navigation principles, repurposed for the most advanced journey ever attempted. As they approached the moon, they had to execute a critical engine burn to slow down enough to be captured by lunar gravity. This was the service module's service propulsion system engine, a single large engine that the crew's lives depended on absolutely. If it didn't fire, they'd swing around the moon and head back toward Earth on a free return trajectory, scary but survivable. If it fired but didn't shut off at the right time, they could crash into the lunar surface or be flung into a useless orbit. And here's what made it especially nerve-wracking. The burn had to happen on the far side of the moon, out of radio contact with Earth. Mission Control would simply lose the signal as Apollo 8 disappeared behind the moon, and then they'd wait. If the burn worked, the signal would come back at a predicted time. If it didn't work, the signal would come back at a different time, or not at all. so everyone on Earth just waited in silence, watching clocks. The burn worked perfectly. 20 minutes of radio silence, and then Jim Lovell's voice crackled through. "Go ahead, Houston." They were in lunar orbit, and what they saw took their breath away. The lunar surface up close was stark and ancient, a landscape of craters and shadows untouched by atmosphere or weather for billions of years. Bill Anders later described it as a dirty beach, not the romantic silver globe of poetry, but something rawer, more real. And then, on their fourth orbit, as they came around the limb of the moon, they saw something no human had ever seen before: Earth rising over the lunar horizon. Anders grabbed a camera. He actually had to ask for color film. They'd been shooting in black and white, and took what became one of the most famous photographs in history. Earthrise. This small, luminous blue marble hanging in the blackness, impossibly fragile, impossibly beautiful. That single image did something that no amount of engineering data could do. It changed how humanity saw itself. It's often credited as one of the catalysts of the modern environmental movement. This sudden visceral understanding that our world is finite, that it floats alone in an enormous darkness, that there is no backup. On Christmas Eve, the crew read from the book of Genesis during a live television broadcast. In the beginning, God created the heavens and the earth, and an estimated 1 billion people listened. It was one of the largest audiences in television history up to that point. And then they fired that engine again, on the far side of the moon once more, and headed home. The re-entry was nominal, the splashdown on target. Apollo 8 proved that the entire architecture worked: navigation, communication, life support, the service propulsion engine, the heat shield at lunar re-entry speeds, which were significantly faster than orbital re-entry. Everything the crew needed to get to the moon and back had been validated, except for the actual landing part. Apollo 9 tested the lunar module in Earth orbit in March 1969, and Apollo 10 took the lunar module all the way to the moon and descended to within about 50,000 feet of the surface, close enough to scout the landing site, but not to land. The crew of Apollo 10, Tom Stafford and Gene Cernan in the lunar module, actually experienced a brief moment of genuine terror when the ascent stage began spinning wildly during the staging sequence. Cernan later said some words on the radio that were decidedly not suitable for broadcast. But they regained control and rendezvoused successfully with John Young in the command module. Everything was ready. And so we arrive at July 1969 and Apollo 11. You know the names: Neil Armstrong, Buzz Aldrin, Michael Collins. But let's talk about what actually happened from an engineering standpoint, because the reality was far more harrowing than the smooth narrative most people remember. The Saturn V launched on July 16th from Pad 39A at Kennedy Space Center. The ascent was nominal. The translunar injection burn sent them toward the moon. 3 days of coasting, mid-course corrections, the usual routine. If you can call traveling 250,000 miles through space routine. On July 19th, they entered lunar orbit. And on July 20th, Armstrong and Aldrin crawled through the tunnel into the lunar module named Eagle, sealed the hatch, and separated from the command module Columbia, where Collins would orbit alone, the loneliest human being in the universe, out of contact with everyone every time he swung behind the moon. The powered descent to the surface is one of the most dramatic sequences in the history of technology. The descent engine on the lunar module was throttleable, which was unusual for rocket engines of that era. Most engines were either on or off. This one could be adjusted from about 10% to full thrust, giving the crew fine control during landing. The engine was built by TRW, and its design was elegantly simple in some ways. It used hypergolic propellants, meaning the fuel and oxidizer ignited on contact. No ignition system needed. Reliable, no spark plugs to fail. But as Eagle descended, things started going wrong. At about 30,000 feet, program alarms began flashing on the computer display. 1,202 alarms, then 1,201 alarms. These were executive overflow alarms, meaning the computer was being asked to do more tasks than it could handle simultaneously. The problem, it turned out, was partly caused by the rendezvous radar being left on. It was feeding data to the computer that wasn't needed during descent, consuming processing cycles. In mission control, a 26-year-old guidance officer named Steve Bales had to make an instant call: abort or continue. He'd studied these alarm codes. He knew that the computer's software, Margaret Hamilton's software, was designed to prioritize. When overloaded, it would shed lower priority tasks and keep running the essential ones: guidance, navigation, engine control. Bales called go. Flight Director Gene Kranz confirmed. They pressed on. And then Armstrong looked out the window and realized the computer was guiding them toward a boulder field. The planned landing site was strewn with rocks the size of cars, right at the rim of a large crater. Not survivable for a landing. So Armstrong did something that only a test pilot of his caliber would do. He took semi-manual control, flying the lunar module like a helicopter, skimming over the boulder field, looking for a clear spot. The fuel gauge was dropping. Mission Control called out the remaining propellant. 60 seconds, then 30 seconds. At 30 seconds of fuel remaining, if they hadn't landed, they would have had to abort, fire the ascent engine, and abandon the landing. Armstrong found a clear patch, brought Eagle down, and Aldrin called out the final descent data: contact light. As a probe dangling from one of the landing legs touched the surface, Armstrong shut down the engine. Houston, Tranquility Base here. The Eagle has landed. Charlie Duke, the capsule communicator in Houston, responded with a voice tight with emotion. Roger. Tranquility. We copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again. They had about 17 seconds of fuel remaining. 17 seconds between success and abort. Some post-flight analysis suggested it might have been slightly more. The fuel quantity gauges weren't perfectly precise, and propellant was sloshing in the tanks. But regardless, the margins were razor thin. 6.5 hours later, Armstrong opened the hatch and descended the ladder. The famous words, the small step, the giant leap. Aldrin followed. They spent about 2.25 hours on the surface, planted a flag, set up a few scientific instruments, collected about 47 pounds of lunar samples, and took photographs. The surface was covered in a fine, powdery regolith that stuck to everything: their suits, their gloves, their equipment. Aldrin described the landscape as magnificent desolation. They could see the curvature of the moon's horizon, much closer than Earth's because the moon is so much smaller. The sky was utterly black, even with the sun blazing. No atmosphere to scatter light. But here's a detail that doesn't get talked about enough. The ascent from the lunar surface was, in some ways, the most terrifying moment of the entire mission. The ascent engine on the lunar module had to work. There was no backup, no redundancy. If that engine didn't fire, Armstrong and Aldrin would die on the moon, and there was absolutely nothing anyone could do about it. The engine was as simple as engineers could make it. Hypergolic propellants, pressure-fed, minimal moving parts. It had been tested extensively on Earth, but it had never been fired on the moon. When Aldrin pressed the button, the engine lit, and the ascent stage rose from the surface, leaving the descent stage behind as a launch platform. It worked. But the sheer vulnerability of that moment, two humans on another world, their lives depending on a single engine ignition with no alternative. That's the kind of risk that's hard to fully appreciate from the comfort of hindsight. They rendezvoused with Collins, transferred back to Columbia, jettisoned the lunar module, and headed home. Re-entry, splashdown, recovery by the USS Hornet. The crew was quarantined for 3 weeks in case they'd brought back lunar pathogens, a precaution that seems almost quaint now, but was taken very seriously at the time. And the world celebrated. An estimated 600 million people had watched the landing on television. It was, and remains, one of the singular achievements of human civilization. But Apollo didn't stop there, and the missions that followed are in some ways even more interesting from an engineering perspective, because they pushed the hardware further and dealt with problems that tested every system to its limits. Apollo 12, 4 months later, demonstrated pinpoint landing accuracy. Pete Conrad set the lunar module down within walking distance of Surveyor 3, an unmanned probe that had landed 2.5 years earlier. They actually retrieved parts of Surveyor to bring home for analysis, to see how the hardware had weathered the lunar environment. And then came Apollo 13 in April 1970. And this is a story that reveals something profound about engineering. Not just how you design systems, but how you respond when those systems fail in ways you never anticipated. Because the oxygen tank that ruptured aboard Apollo 13 didn't fail because of some exotic, unknowable flaw. It failed because of a series of small, seemingly insignificant decisions that cascaded together across months and years, the way engineering failures almost always do. The tank in question was oxygen tank number 2 in the service module. And here's where the chain starts. That particular tank had originally been installed in the service module for Apollo 10, the dress rehearsal mission we talked about earlier. But during manufacturing, it was removed for modification, and during that removal, it was accidentally dropped about 2 inches. 2 inches. Not a dramatic fall. Nobody thought much of it. The tank was inspected, appeared fine, and was eventually installed in the Apollo 13 service module instead. But that small drop may have loosened a fill tube inside the tank, which would matter later. Then, during a pre-launch test at Kennedy Space Center, ground crews tried to empty the tank and couldn't get all the oxygen out. The tank had been designed to operate with 65-volt heaters internally, but the ground support equipment at the Cape had been upgraded to use 65 volts, while the thermostat switches inside the tank were still rated for the original 28-volt spacecraft power. When they ran the heaters at the higher voltage to boil off the remaining oxygen, the thermostats welded shut. The heaters ran far too hot, probably reaching around 1,000 degrees Fahrenheit inside the tank, damaging the Teflon insulation on the internal wiring. Nobody knew. The temperature gauge only read up to about 80 degrees, so everything looked normal on the readouts. The tank passed its tests, was loaded with oxygen, and flew. 55 hours and 54 minutes into the mission, on April 13th, 1970, astronaut Jack Swigert flipped a switch to stir the cryogenic oxygen tanks, a routine procedure to prevent stratification of the super-cold liquid oxygen inside. When the fans in Tank 2 activated, the damaged wiring sparked. The Teflon insulation caught fire in the pure oxygen environment. Pressure built up rapidly, and the tank ruptured. The explosion damaged the adjacent oxygen tank 1 as well, and within about 3 hours, all the oxygen in the service module was gone. And here's what you have to understand. Those oxygen tanks weren't just for breathing. The The fuel cells that generated all of the command module's electrical power worked by combining hydrogen and oxygen. No oxygen meant no fuel cells, which meant no electricity, no water production, no heat. The command module, Odyssey, was dying. Commander Jim Lovell, Jack Swigert, and Fred Hayes were about 200,000 miles from Earth, heading toward the Moon in a spacecraft that was rapidly losing the ability to sustain life. And this is where the engineering response becomes extraordinary, because the solution wasn't some brilliant single fix. It was dozens of people on the ground working hundreds of small problems simultaneously, improvising with what the crew had available, and doing it all under a time pressure that left almost no margin. The first critical decision was to use the lunar module, Aquarius, as a lifeboat. The lunar module had its own oxygen supply, its own batteries, its own life support. It had been designed to keep 2 people alive for about 45 hours on the lunar surface. Now it needed to keep 3 people alive for roughly 90 hours in deep space. The math didn't work cleanly, but it was the only option. So they powered down the command module almost completely, preserving its re-entry battery for the very end, and moved into the lunar module. But problems multiplied. The lunar module's carbon dioxide scrubbers were designed for 2 people, not 3. Carbon dioxide levels began to rise. The command module had plenty of spare lithium hydroxide canisters for scrubbing CO2, but they were square. The lunar module's receptacles were round, literally square peg, round hole. So engineers on the ground, working in a room at mission control, had to figure out how to build an adapter using only materials the crew had on board: cardboard from flight plan covers, plastic bags, duct tape, hoses from the spacesuits. They talked the crew through building it step by step. It worked. It was ugly, but it worked, and the CO2 levels came back down. Then there was navigation. The explosion had knocked debris all around the spacecraft, and the crew couldn't use star sightings for navigation because they couldn't distinguish stars from the glittering particles of debris surrounding them. They had to use the sun for alignment instead, a procedure that had been developed but never really expected to be needed. They had to perform precise engine burns using the lunar module's descent engine, an engine designed to land on the Moon, now being used as a course correction rocket for a trajectory that would swing them around the Moon and back toward Earth. The first burn put them on a free return trajectory. A second burn, after they'd swung around the Moon, sped up their return and adjusted their re-entry angle. These burns had to be timed perfectly and aimed precisely, and the crew was cold, exhausted, and working in a spacecraft that was never designed for this kind of flying. The cold was a real problem. With almost all systems powered down to conserve electricity, the cabin temperature dropped to around 38 degrees Fahrenheit. Water condensed on every surface. The crew couldn't sleep. Hayes developed a kidney infection. And through all of this, they had to stay sharp enough to execute procedures that had been developed in real time by hundreds of engineers on the ground. Procedures that had never been tested, never been simulated, written up on the fly, and read up to the crew over the radio. And here's the thing that really gets me about Apollo 13. The mission is often called a successful failure, and that phrase captures something important about engineering philosophy. The spacecraft failed. The mission objective, landing on the Moon, was not achieved. But the crew came home alive, and they came home alive because the engineering culture at NASA, for all its flaws, had built in enough redundancy, enough flexibility, and enough sheer problem-solving capability that people could improvise their way out of a catastrophe that nobody had specifically planned for. The lunar module was never designed to be a lifeboat. The square canisters were never meant to fit in round receptacles. The descent engine was never intended for deep space navigation burns. But the systems were understood deeply enough by enough people that they could be repurposed, recombined, and pushed beyond their design envelope when survival demanded it. That's what good engineering culture gives you. Not perfection, not the absence of failure, but the ability to respond when failure comes. Apollo 13 returned safely on April 17, 1970. The crew jettisoned the service module before re-entry, and for the first time, they could see the damage. An entire panel blown away, wiring and equipment exposed. Lovell later said it looked like the ship had been hit by a bomb. They powered up the command module, using a special checklist that had been developed during the crisis to bring systems online in the right sequence, using minimal power, transferred back from the lunar module, jettisoned Aquarius, and re-entered the atmosphere. Splashdown in the Pacific. All 3 crew members safe. But Apollo 13 had a chilling effect. The American public, which had already been losing interest in moon missions after the triumph of Apollo 11, now confronted the reality that these flights were genuinely dangerous. Congress was already cutting NASA's budget. 3 planned missions, Apollo 18, 19, and 20, were canceled. The remaining flights, Apollo 14 through 17, would have to carry the full weight of lunar scientific exploration. And those later missions are genuinely fascinating because they represent the maturation of Apollo from a flags and footprints demonstration into a real scientific program. Apollo 14, in early 1971, sent Alan Shepard, the same Alan Shepard who'd made that first 15-minute suborbital flight a decade earlier, to the moon. He was 47, the oldest person to walk on the lunar surface during Apollo. He famously hit 2 golf balls with a makeshift 6-iron, but more importantly, the mission demonstrated improved navigation and carried a more extensive suite of scientific instruments. Apollo 15, though, was the real turning point. Launched in July 1971, it was the first of the J missions, extended stays with a much heavier focus on science. The crew, Dave Scott, Al Worden, and Jim Irwin, spent 3 days on the surface at Hadley Rill, a sinuous channel near the Apennine Mountains, and they had a new tool that changed everything, the Lunar Roving Vehicle. Think about that for a second. NASA put a car on the moon. It was an electric vehicle, about 10 feet long, with a top speed of maybe 8 miles per hour, powered by 2 36-volt silver-zinc batteries. Each wheel had its own electric motor. It folded up and was stowed in the descent stage of the lunar module, then unfolded on the surface like an elaborate piece of origami. And it extended the range of exploration enormously. Instead of walking a few hundred meters from the landing site, astronauts could drive kilometers, collecting samples from geologically diverse locations. Scott and Irwin drove over 17 miles across the lunar surface during their 3 EVAs. They collected 170 pounds of samples, including what became known as the Genesis Rock, a piece of anorthosite estimated to be over 4 billion years old, a fragment of the moon's original crust. And during one of the most elegant demonstrations in the history of science education, Dave Scott stood in front of the television camera, held out a hammer in one hand and a falcon feather in the other, and dropped them simultaneously. In the vacuum of the moon, with no air resistance, they hit the ground at exactly the same time. Galileo had predicted this nearly 4 centuries earlier, and now here it was, proven on the surface of another world for anyone watching back home to see with their own eyes. Scott let go, and the hammer and the feather fell together in that eerie, airless silence, landing in the dust at the same instant. "How about that?" Scott said, with this quiet satisfaction in his voice. Mr. Galileo was correct in his findings. It's one of those moments that doesn't need commentary. 400 years of physics, confirmed in the most dramatic classroom imaginable. Apollo 15 was a mission that made scientists genuinely giddy. The samples alone reshaped our understanding of lunar geology. But it also showed that the program had matured. This wasn't about flags and footprints anymore. This was real fieldwork, real exploration, the kind of methodical investigation that Tsiolkovsky and Goddard and all those early dreamers had imagined when they talked about humanity reaching other worlds. The astronauts weren't just visitors. They were becoming geologists, field scientists, working a terrain that no human had ever studied up close. Apollo 16 followed in April 1972, with John Young, Ken Mattingly, and Charlie Duke heading to the Descartes Highlands. Now, Young was already a veteran. He'd flown Gemini missions. He'd orbited the moon on Apollo 10. The man had more spaceflight experience than almost anyone alive, and the Descartes region was chosen specifically because scientists believed it would contain volcanic rocks, which would tell a different story about the moon's geological history than the mere basalts they'd already collected. Here's the thing, though. When Young and Duke actually got there and started collecting samples, the rocks weren't volcanic at all. They were breccias, impact-formed rocks created by ancient collisions. The entire geological hypothesis that had driven the landing site selection turned out to be wrong. And that's actually wonderful, if you think about it. That's science working exactly the way it's supposed to. You form a hypothesis, you go test it, and sometimes the moon tells you something you didn't expect. The Descartes samples forced a significant revision of lunar geological models, and that revision was more valuable than confirmation would have been. Young and Duke also drove the rover extensively, about 16 miles total, and Duke left a family photograph on the surface, wrapped in plastic, a little portrait of his family sitting there in the lunar dust. It's probably still there. The ultraviolet radiation has almost certainly bleached it blank by now, but it's there, this tiny human artifact in the most inhuman of landscapes. And then came Apollo 17, December 1972. The last one. Let's sit with that for a moment, because it deserves some space. Apollo 17 was the final crewed mission to the moon, and as of right now, more than 50 years later, no human being has been back. When Gene Cernan stepped off the lunar surface for the last time, he didn't know he was closing a chapter that would stay closed for decades. Nobody did. Most people assumed we'd be back within a few years, that the moon was just the beginning, that Mars was next, that space stations and lunar bases were inevitable near-term developments. The future felt wide open. The crew was Gene Cernan, Ron Evans, and Harrison Jack Schmitt. And Schmitt is notable because he was the only professional scientist, a geologist with a PhD from Harvard, to walk on the moon during the entire Apollo program. Every other moonwalker was a test pilot or military aviator first. The scientific community had lobbied hard to get a trained geologist on a mission, and Schmitt was their champion. He'd been training for years, and his inclusion on Apollo 17 was a kind of vindication for the idea that space exploration should serve science, not just demonstrate national capability. They landed in the Taurus Littrow Valley, a site chosen for its geological complexity. It had both ancient highland material and what appeared to be relatively young volcanic deposits. And Schmidt's geological training paid off almost immediately. During the second EVA, he spotted something extraordinary: orange soil, bright, vivid orange, sitting just beneath the gray surface dust. "It's orange!" he shouted over the radio, and you can hear the genuine shock in his voice on the recordings. Cernan thought he was joking at first, but Schmitt was right. They'd found orange glass beads, tiny spheres of volcanic glass that had been erupted from deep within the moon. roughly 3.7 billion years ago. These beads contained volatile elements, zinc, lead, sulfur, in quantities that nobody had expected to find on the moon. They became some of the most scientifically significant samples of the entire Apollo program, and they're still being studied today with instruments that didn't exist in 1972. Apollo 17 set records across the board. Longest time on the lunar surface, just over 3 days. Longest total EVA time, over 22 hours outside. Most lunar samples returned, about 243 pounds. Longest distance driven on the rover. It was, in every measurable way, the most productive lunar mission ever flown. And then, it was over. Cernan climbed the ladder of the Lunar Module Challenger for the last time, and before he did, he said a few words. "We leave as we came," he said, "and God willing, as we shall return, with peace and hope for all mankind." The ascent engine fired, the upper stage lifted off the surface, and humanity's last footprints on another world were left behind in the dust. The Saturn V flew once more after that, but without a crew bound for the moon. In May 1973, a modified Saturn V launched Skylab, America's first space station, into orbit. And this is a story that deserves telling because it's another one of those brilliant improvisations that NASA had become so good at. Skylab was essentially the third stage of a Saturn V, the S-4B stage, converted into a habitable workshop. The idea was elegant. Instead of launching an empty shell and then filling it, you take the hydrogen tank of a rocket stage that's already enormous, gut it, outfit it with living quarters and scientific instruments, and launch the whole thing in one shot. But during launch, things went wrong almost immediately. About 63 seconds into flight, the meteoroid shield, which also served as a thermal shield, tore away from the station. And as it ripped off, it snagged one of the two main solar array wings and tore it completely off. The other solar array was jammed by debris and couldn't deploy. So Skylab reached orbit with almost no electrical power and no thermal protection. The interior temperature started climbing toward 130 degrees Fahrenheit. The station was, by any reasonable assessment, crippled before it even began. The first crew, Pete Conrad, Joe Kerwin, and Paul Weitz, launched 11 days later, and their first job wasn't science. It was rescue. They performed one of the most remarkable repair missions in spaceflight history. They deployed a parasol sunshade through a small scientific airlock, essentially threading an umbrella through a hole in the side of the station and opening it up to shade the hull from direct sunlight. The temperature dropped. Then, during a daring EVA, Conrad and Kerwin freed the jammed solar array using a combination of tools including, famously, a pair of bolt cutters attached to a long pole. The array swung open, power flowed, and Skylab came to life. 3 crews occupied Skylab over the course of 1973 and 1974, spending 28, 59, and 84 days in orbit, respectively. That last crew, Jerry Carr, Ed Gibson, and Bill Pogue, spent nearly 3 months in space, setting an American endurance record that would stand for decades. And the science was extraordinary. Skylab carried the Apollo telescope mount, a sophisticated solar observatory that captured over 175,000 images of the sun. It conducted materials science experiments, Earth observation studies, and extensive biomedical research on the effects of long-duration spaceflight on the human body. It proved that people could live and work in space for months at a time, which was a question that genuinely hadn't been answered yet. But Skylab also taught a subtler lesson about the relationship between ground controllers and crews in space. The third crew, at one point, essentially went on a quiet work strike. They'd been overworked, micromanaged, with every minute of their day scheduled by mission control. They pushed back, negotiated more autonomy, more personal time, more control over their own schedules, and productivity actually improved afterward. It's a lesson that echoes through every long-duration spaceflight program, since you can't treat astronauts like machines. They're people, and the psychology of isolation and confinement matters as much as the engineering of life support systems. Now, while all of this was happening on the American side, the Soviet program had taken a different path entirely. After losing the moon race, the Soviets pivoted to space stations with remarkable commitment. The Salyut program launched a series of stations through the 1970s, and cosmonauts accumulated long-duration spaceflight experience that far exceeded anything the Americans were doing. This eventually culminated in Mir, which launched its core module in 1986 and remained continuously occupied for nearly 10 years. Mir was a modular station. New sections were launched and docked over time, expanding its capabilities. It was cramped, it was aging, it occasionally caught fire or leaked atmosphere, but it worked. And the experience the Soviets and then the Russians gained from operating Mir was absolutely essential to what came next. Because what came next was the International Space Station, the largest structure humans have ever built in space, a collaboration between the United States, Russia, Europe, Japan, Canada, and other partners. The first module, Zarya, a Russian-built component funded by the United States, launched in November 1998. 2 weeks later, the Space Shuttle Endeavour carried up the Unity node and connected the two pieces together. And from those first 2 modules, the station grew, piece by piece, mission by mission, into a sprawling complex the size of a football field, orbiting about 250 miles above the Earth, moving at 17,500 miles per hour, completing an orbit every 90 minutes. The ISS has been continuously occupied since November 2000. Think about that. For more than 2 decades, there has not been a single moment when all humans were on Earth. Someone has always been up there, circling overhead, living and working in microgravity. It's become so routine that most people forget it's happening, which is, in its own way, one of the greatest achievements in the history of engineering, making the extraordinary ordinary. And here's where the story curves back toward something that would have felt familiar to Goddard and Tsiolkovsky and all those early pioneers. Because after decades of space exploration being the exclusive domain of governments, the 21st century brought something genuinely new. Private companies building their own rockets, their own spacecraft, their own visions of what space could be. SpaceX, founded by Elon Musk in 2002, started from almost nothing. A small team, a lot of ambition, and a series of early failures that nearly destroyed the company. Their first 3 Falcon 1 launches failed. They were almost out of money. And then the 4th flight, in September 2008, reached orbit, and everything changed. From there, SpaceX developed the Falcon 9, a medium-lift rocket that became the workhorse of the commercial launch industry. And then they did something that most aerospace engineers had considered impractical or even impossible. They landed the first stage of an orbital rocket back on the ground, upright, ready to be refurbished and flown again. The first successful landing was in December 2015, and it was a genuine paradigm shift. Reusability had been the holy grail of rocketry since the very beginning. The space shuttle had attempted it with mixed results, but SpaceX made it routine. They've now landed and reflown boosters dozens and dozens of times, driving down the cost of access to space in ways that are reshaping the entire industry. Blue Origin, Rocket Lab, and other companies have joined the landscape, each approaching the problem differently. And NASA itself has evolved, shifting from building everything in-house to purchasing services from commercial providers, buying rides to the space station rather than building the vehicles itself. So here we are. More than a century after Tsiolkovsky sat in his log cabin in Kaluga, scratching out equations about rocket propulsion, and more than 50 years since Gene Cernan left the last human footprints on the moon. The Artemis program is working to return astronauts to the lunar surface. The James Webb Space Telescope is peering deeper into the universe than any instrument before it. Robotic missions are crawling across Mars, orbiting Jupiter's moons, sailing past the edge of the solar system. And if you zoom out, way out, and look at the whole sweep of this story, from Tsiolkovsky's equations to Goddard's frozen field in Massachusetts, to von Braun's V2s, to Korolev's Sputnik, to Gagarin's single orbit, to Armstrong's boot print, to the space station gliding silently overhead right now, what you see is something deeply human. Every step was built on the one before it. Every breakthrough carried the fingerprints of 100 earlier failures. Every rocket that flew carried the accumulated knowledge of everyone who'd ever tried and failed and tried again. The engineering is magnificent. The turbo pumps and the heat shields and the guidance computers and the life support systems and the lunar rovers and the solar arrays. But underneath all of it, always, are people. People who looked up at the sky and refused to accept that it was out of reach. People who did the math, bent the metal, ran the tests, took the risks. Some of them became famous, most of them didn't. But every one of them added something to this extraordinary ongoing project of reaching beyond our own world. And that project isn't finished. It's barely begun, really. But for now, tonight, it's enough to know that it's happening. That somewhere above you, right now, the space station is crossing the sky, and someone is up there, looking down at the Earth, watching city lights slide beneath them in the darkness. And somewhere, in a lab or a factory or a university office, someone is working on the next piece of the puzzle, the next engine, the next material, the next mission. They're building on everything that came before, just like Goddard built on Tsiolkovsky, and von Braun built on Goddard, and everyone who came after built on everyone who came before. That's how it works. That's how it's always worked. One step, then another, then another. And the sky, it turns out, was never the limit. It was just the beginning. So let that thought settle in, and let your breathing slow, and let the quiet hum of all those engines and all those dreams carry you gently off to sleep.